Okay, welcome back. It's Friday. It's foggy out. I thought maybe I would start with an idea, just kind of summarize some of the things I've been saying for a few days. I think I can start with just a cubic function. Check this out. I might get to your questions in a second. If I just start with a cubic function, can I really just make up any old cubic function? I'm worried now. I'm worried. I thought maybe we could illustrate sort of all the ideas that we've been discussing for a few days, all in one problem here, I think. So the first idea was, let's look for critical numbers, or what is a critical number, and anyway, let's look for them. So you know what a critical number is. It's those numbers that make the first derivative 0 or undefined. So let's look for some critical numbers. So I need a first derivative. So that's easy enough. These derivatives are kind of easy. 6x squared minus 8x minus 11. Okay. And so now if I'm looking for critical numbers, of course, now I could ask myself this question: when is the derivative undefined? And of course the answer is never. But what I really need then is, when is the derivative 0? So I'll work on that. When is this derivative 0? I guess that might require a quadratic formula, unless I got lucky in this factor somehow. Probably not. So I think I'll try to quadratic formula. On your mark, get set, go. This is what happens. This might get nasty, right? Because I just made this up. Anyway, here we go. Quadratic formula: negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. That's the quadratic formula. And this is 8 plus or minus 64 plus something huge. Huh. All right, 328. This is the square root of 328 all over 12. I could work on simplifying the square root of 328. I don't know if I really care. Let's call these our critical. Can we call these our critical numbers? These are my critical numbers.
Wouldn't you want to simplify 8?
Well, that's what I just argued about with myself. I don't want to simplify damn square root. I don't feel it's Friday. I don't feel like it. No, I don't know. In an algebra class, I'm probably worried about you simplifying square roots. In calculus class, at some point we reach a maturity level where we just want the answers. We don't care how simplified they are sometimes. You know what I mean? But I would like to, now what do I want to do? So these are my critical numbers. There's 2 of them, right? There's 2 of them. And I think I want to test to see if they're mins and maxes. I want to know who's a min and who's a max. Or maybe they're neither, you know? Mins or maxes or neithers. That's what critical numbers are. And I got a test for that. It's called the first derivative test. It's kind of a process. And I've tried to teach you that process. Let's do it. The process involves sort of drawing a number line. I like to label the number line f prime. And then I like to put my critical numbers on the number line. And because they're kind of nasty little critical numbers, I'm not sure what they are. We could estimate them with approximate calculator decimal approximations. That would be helpful. Could you help me do that? Just what is the square root of 328 plus 8 divided by 12? And what is the square root of 328 subtracted from 8 plus 12 divided by?
The decimal
Yes. Yes.
If you do the plus, it's 2.175.
Okay, I'm gonna call that 2.2 approximately. All right.
And minus is 0.842.
A 0.842. Okay, we'll call that a 0.8. 4. All right.
It's also a negative point.
Oh, it's negative?
Oh, sorry.
That's all right. All right. So those are my two numbers. That's what those are, huh? Thank you. I mean, I like stuff listed exactly, but these are pretty nasty. They're listed exactly, but then for the purposes of putting them on the number line, I'll use these approximations. So one of them is approximately a 2.2. The other one is approximately a negative 0.84. And now what we learned was we would test each region in between. These are my critical numbers. And by the way, the value of the derivative at these points, the value of the derivative at these points was 0. That was the point. The value of the derivative in between these points is now what I'm interested in. So I test some numbers in these regions. So I'll go way out here and pick a 3 for a test number. Let me kind of make this nice and bold so I don't get confused. I don't want to get confused who's my test numbers and who's my critical numbers. So anyway, that little 3 is a test number, and what I do with that test number is I plug it into the derivative, and I just really want to know if the derivative's positive or negative. Because that tells me if the derivative's positive or negative, it tells me the function is increasing or decreasing. Right, big theme from the last couple days, right. So cool, let me do that. I'm plugging a 3 into my derivative. And here's my derivative. I think it's positive. So that whole region is positive, and in that region, the function is increasing. What about in here? I'll pick a 0. I'll pick a 0. I'll plug it into the derivative. It's pretty easy. It's a negative 11. It's negative is the point. That means it's decreasing. Let's go over here. We'll pick a negative 1. I'll plug it in the derivative. Positive 6 plus 8 is 14 minus 3. I think I get a positive. And it's increasing. So this is awesome. I just learned some stuff about my critical numbers. I had these two critical numbers. I approximated them with decimals, but now I just learned that this one is a max. And how do you know it's a max? Because what we have up here is sort of code here, or shorthand notes here, that tell me the function is increasing and then decreasing. And around a critical number, if it's increasing and then decreasing, it must have hit a max, I guess. And then it's decreasing and then increasing, so it must have hit a min. This other one is a min. So it's very logical. It's not really supposed to be mysterious. I try to explain the logic of what we're doing here. So cool, we just found a max and a min. Okay, I'm going to keep going. So now, here's the deal. That whole game I just played was called, I call that the first derivative test. I mean, actually, that's what it's called. And the first part of the game was find some critical numbers. So we found some critical numbers. But then to test the critical numbers, it involved this thing called the first derivative test. So that's what we did. Okay, guess what? Now I want to play that whole game again on the second derivative. Same exact game, really. So here we go. So now I want the second derivative. The second derivative is, well, hey, the second derivative, what? That's all right. The second derivative is 12x minus 8. I want to play the same game, which means when is this undefined? Never. When is it 0? Oh, we'll figure that out. When is this 0? When is this 0? Move the 8 over, divide by 12. 2/3, I guess. 8 12ths or 2/3. 8 12ths or 2/3. Cool. Now this came from the second derivative, so we don't call it a critical number. It's sort of just language. It could be called. It's not a critical number. Critical numbers come from the first derivative, so we don't use that language. We think what it is an inflection point, but at the moment we call it a possible inflection point because I'm not sure yet. So it's a possible inflection point, or maybe a PIP. Okay, that's what he is. He's a possible inflection point. All right, so how do I prove and decide if he really is an inflection point? I play this game again, this number line game again. So I'm going to do this game again. This time I label the number line F double prime. And I put my possible inflection point on the number line, and I play the game again using the second derivative. You'd be tempted to call this game again using the second derivative. You'd be tempted to call it a second derivative test, but that's not what it's called. So let's not call it that. I want to call it a concavity test. So that's what we're doing now. All right, so here it's the same game though. What is it? I'm putting the 2/3 on that number line. By the way, I sort of try to line it up so 2/3 would roughly be here. That's my 2/3, lined up with that number line. Anyway, and then I try to pick something out there in that region, and I test to see if the second derivative is positive or negative. Now, so anyway, I'm picking a 1. Picking a 1. I go to my second derivative. I plug in a 1, and it's positive. When the second derivative is positive, I'll put some little positive things here, but when the second derivative is positive, what that tells me about the function is concave up. That's true. And I tried to convince you of that last class, but you can just believe it now if you want. The first derivative tells me that the function is increasing or decreasing. The second derivative tells me whether the function is concave up or concave down. So it's positive, so it's concave up. And my little note for that would be a picture like this. It tells me it's concave up. I'm not trying to imply increasing or decreasing here. I'm not. I'm trying to imply just concave up. The truth is, if I look above me up there, that tells me about the increasing and decreasing up there. But this is telling me about the concavity of the function, of the original function. I know about the increasing and decreasing, and I know about the concavity of the original function by analyzing these derivatives. Let's go over here. We'll pick a 0. Is that cool? Yep. And I'll plug it into the second derivative. And when I plug a 0 in the second derivative, it's -8. It's negative. So it's negative. And that means it's concave down. The function is concave down. So that's pretty awesome. I'm going to circle this now. See, I was worried. I told you it was a possible inflection point. It's not an official inflection point unless it really does change concavity, which it did. So now I know it's an official inflection point. So I'm going to call it an inflection point. Yeah, I guess I just tested it and found out it was an inflection point for.
If it didn't change concavity.
It's an interesting point still, but it ain't. If it doesn't change concavity, please don't call it an inflection point. Right.
And you plug it in. You plug the possible point into the second derivative. Find out the concavity up or down. Not this point. I put this point on a number line and I tested around it. Got it.
So I plugged a 1 into the second derivative, and I plugged a 0 into the second derivative, right? On a test or a quiz, I probably have a little place for you to. I want you to, after you do all this beautiful work, I want to see all this beautiful work, and then. Is there a relative min? Is there a relative max? Is there any inflection points? And maybe I would like you to sort of officially list them for me. And when we list them, it becomes a little pain here because to list them, I think I'd like them listed as points. They are points. And so I want their x and y value. And that is a pain with these. These are pretty nasty little x values, right? So do you think I want you to actually plot this exact x value into the original function? Do you think I want you to take 8 plus the square root of 328 over 12 and cube it? No, not exactly. I do not. Right. I mean, it became, you know, if this was a 2, you could plug a 2 in there and cube it, and you could find the y value. But because these are pretty nasty x values, I don't really want you to find an exact y value. I don't. I tell you what, though. Let's sort of do this approximately then, okay? Because these are kind of rough and nasty. By the way, though, I see your work. I see your exact work. But then, for the purposes of listing them here, let's. I might need to use these decimals. By the way, was there a min? You know, if there's not a min, you should write none here. If you know, sometimes there's not an answer for what I ask for, and you write none, or ain't none. That means there is some. Don't do that. You put ain't none, never. All right, where am I? Is there a min? Oh, yeah, there's a min. It's approximately, the x value is approximately 2.2. If I want the y value, I'm going to plug that in, and it'll be an approximate y value. Can you help me with that? Anybody got the gumption to plug a 2.2 in there? Or are you going to make me do it? There's a relative max. There's a relative max at this negative 0.84. That's my approximate x value there, but I'm going to use that approximate x value, and I'm going to plug it in and find an approximate y value. That's my min and my max, and I think I want these y values so I can plot them accurately, semi-accurately. So if you could help me plug those in, I'd appreciate it. So for this min, negative 7.3?
Yeah.
Okay, thank you very much. By the way, did we ever find an inflection point? Did we actually officially find an inflection point? Yeah, it was 2/3, right. And so that's the x value. I'd like to find the y value. Again, what am I doing to plot y values? I'm just going back to the original function and plugging in x's and plotting y's. I mean, this is me plotting points. Please don't get confused with all the testing I was doing. You know, with my testing, I was plugging things into the derivative. I was plugging things into the second derivative. That was testing these regions. But now that I'm plotting points, I'm plugging things into the original function, of course. Anybody got an answer for this? 20.2? 20.2, thank you. You could do the 2/3 exactly if you had some guts. 2/3 cubed, everybody knows what that is. 2/3 squared, everybody knows what that is. 2/3 here, plus 15, oh my God. That's 8, that's 16/27 minus 16/9 minus 22/3 plus 15. I guess you could get a common denominator of 27 and add all that up. 175 over 27. Okay, thank you. Hey, so what is that approximately? 6.5. Okay, thank you very much. How are you guys doing? All right. So this is a great classic test question in a way. It's a lot of work, but I didn't pick the hardest, craziest function in the world. I just went with a cubic function. But a cubic function is good. It tends to have a min and a max and an inflection point. Hey, you know what? I mean, back from my pre-calculus days, you know what a cubic function looks like from pre-calculus? Especially with a leading coefficient of 2. I don't know, we used to teach students about end behavior. I mean, this is a cubic function that starts low on the left. It probably hits a max, and it hits a min, and you know what I mean? I mean, before I did any calculus, I kind of knew this. A cubic function looks like this. A cubic function with a positive leading coefficient can look like this. It could be upside down if it had a negative leading coefficient. So you got to watch that. But a cubic function with a positive looks like this. So hey, you know what? Maybe I should have known that critical number on the right was the max. On the left. That critical number on the left was the max, and that critical number on the right was the min.
And then in between, somewhere in between, was an inflection point. Do you see that inflection point? I mean, do you see it changing concavity? It's concave down, and then it hits this point, and what does it do? It changes to concave up. That's an inflection point. So a cubic equation is a classic min and max and inflection point problem. It's good. But it's also almost a giveaway if you know what a cubic function looks like. Well, the details aren't given in a way. You got to find the details. By the way, you guys got graphing calculators in your hand. You're allowed to sketch pictures. You're allowed to use them, I think. Again, I have a little issue with using calculators illegally. My tests and quizzes and everything require you to show work. So I'm never interested in just, oh, I'm going to sketch this graph and give him all my answers. I mean, that just doesn't interest me. You know what I mean? You know what I mean. I'm up here teaching and showing you how to do it, so I expect you to do it. But the calculator is there as a tool to help or even confirm some of the stuff you did. And I'm talking just about a basic graphing calculator. I mean, if you use it and sketch this graph, you get a lot of insight into what's going on. What really is illegal is any symbolic calculator work, or if you ever do that, that's really illegal. Hey, we got this. I did want to sketch an official graph, though. I just did a little preview here. Let's do a nice official graph here. Let's see what we got. I'm plotting these points. 2.2, negative 7.3. 2.2, negative 7.3. I like that. Negative 0.84 and 20. Oh, great. Negative 0.84 and way up here about 20. Are you okay with that? And 2/3 and 6.5. 2/3 and 6.5. I'm kind of happy with that. These are these three important points. And now watch what I do. Again, we kind of know the shape, okay? But pretending you don't know the shape, I want to show you this. I read these number lines. I start on the left, and I read what it says to do. Watch. I should increase. Not only should I increase, how should I increase? Concave down. So here I go. I'm starting way out here on the left. I know where I'm headed. I'm going to increase, but while I increase, there's a little concave down look to me. Are you following that? Now what just happened? I hit this point. Okay, cool. So after I hit this point, I start to decrease. Now wait a minute. Look down here. I'm still concave down. I'm still concave down until I hit the inflection point. But anyway, I start to decrease. I'm still concave down until I hit that inflection point. What happens when I hit the inflection point? I switch to concave up. But look above a second. I'm still decreasing. See that? I'm reading both these number lines at the same time, and I'm reading them left to right. This is important. This is how you kind of sketch the graph. I'm reading this information left to right very slowly. I don't think I really practiced this with you. Yeah, what am I doing? Oh, I'm switching concavity. I'm going to be concave up, but I still decrease for a while. Okay, now I'm concave up. That's pretty subtle, dude. That's very subtle. Maybe I could have done something better here. I could have spread out these numbers a little bit. But anyway, I switched to concave up. I hit this minimum. Now, what do I do after I hit this minimum? I start to increase. I'm still concave up. So here I go. And anyway, it's what we predicted, a cubic function. But it's accurate, semi-accurate. This is roughly 20 up here. Yeah, this is roughly negative 7, roughly a 6. Yeah. Cool, huh? I mean, I just got done saying you could use your graphic calculator to get a little hint to see what's happening, but then what I'm really showing you here is how you don't need it, okay? I mean, this thorough calculus analysis of this function puts the graphing calculator obsolete. I mean, I can graph it. You know, you might never have thought of this before. But when you increase, when someone says, okay, you got to increase, then you may never have thought of this before, but the truth is there's 3 ways to increase. Watch. You can increase linearly, like a straight line, or you can increase concave, well, hang on. Sorry. You can increase linearly, like a straight line, or you can increase concave down. That's increasing concave down. Or you can increase concave up. I mean, that's 3, there's only 3 ways to increase. When you draw an increasing graph, it's one of those 3 ways to increase. And again, you may never have thought about that, but it's true. And when you decrease, you can decrease linearly, but you can decrease concave down, or you can decrease concave up. These are all decreasing. Left to right, I'm decreasing. 3 different ways. Okay, I might have more things to say. What about, do you have any homework problems you've been working on that you want me to help you with at all? In 4-1 or 4-3 or you don't do homework? Yes?
Where's 1 is 7 and 10?
And where is that?
We're 226. 4
Okay. This might be good. She just asked me for a homework problem. It's up in 4-3. There's a little group of problems, 107 through 110. So let's just start with, we'll do one of them here. We'll do, maybe I'll try 108 here and see what happens. Now here's what they tell me in 108. There's a long paragraph of directions there, but let me get to the problem. The problem tells me I have a relative min at 0, 0. Okay, I'm not sure I like that, but there's a relative min at 0, 0, and then there's a relative max at 4, 1000. There's a relative max at 4, 1000. That's interesting. So they tell me this about some function. Okay, now there's a long paragraph of directions, like I said. They want me to find a polynomial that has these characteristics. They want me to find the polynomial that has these characteristics. So they help me out. They give me part A. Determine the minimum degree of the polynomial. The minimum degree. Okay, well, I got a min and a max. Could that be a parabola? Could you have a parabola? Can a parabola have a min and a max? I guess not. It can only have a min or a max. So it can't be an x squared. They're asking for the minimum degree. It can't be x squared. It must maybe degree 3. What does a cubic function have? A cubic function might have a min and a max. Okay. So maybe that's the minimum degree. You know, by the way, it could be 4th or 5th, or it could be a higher degree, but I guess the minimum degree might be degree 3. Okay, so maybe I need a degree 3 polynomial here. That seems to be the minimum degree. Polynomial. Hey, can I say one thing about cubic functions? Do all cubic functions have this
No.
max and min?
No.
No, they don't. Not all of them. Yeah. I mean, sometimes you think of a cubic function, you think, okay, yeah, that's real typical. It has a min and a max, and that is pretty typical. But and maybe I said this the other day, but I'll just say it again. Some of them just actually level out right there. You know, and then they really only have one critical number, and it's actually not a min or a max. You know, this one actually has two critical numbers. But you could have this one that's not a min or a max. And then there's actually some that are even stretched out further than that. Watch. There is cubic functions that kind of look like this. They don't even, I mean, they don't really level out right there. They got a little kink in them there, but they're not leveling out. By the way, though, that's an inflection point, I think. Don't you think I'm still changing concavity? So it does have an inflection point. It does have an inflection point. It does have an inflection point. But the mins and maxes can vary on a cubic function. The mins and maxes can vary. Anyway, we think this one's got a min and a max. They told me it has a min and a max. And let's see what else they say here. Part B. Using the fact that the coordinates of the extreme are soluble, but the function and the next coordinates are critical numbers. Yeah. And then use a graphing. Yeah, okay. I got this. All right, so I think it's a cubic function. Let me write a generic, and I think they want me to come up with the cubic function. They want me to find it. Let me write a generic cubic function. You know how to do that? Ax cubed plus bx squared plus cx plus d. There's a generic cubic function. And now it's my job to see if I can find A, B, C, and D that for the cubic function that meets these requirements. Well, shoot. Anybody had any ideas? I mean,
You have to take the derivative.
so she thinks I need a derivative. Let's do a derivative. Let's do a generic derivative. What would be a generic derivative?
3ax squared
3ax squared, that's how you do it.
plus
2bx
plus c.
plus c. And then that derivative of d is gone. Right, because it's a number. Okay. All right, so now what other ideas you got?
Well, the 0, 4, the 0, the x, and the 4, and the max, the x of the max, they make that derivative 0, correct? Am I right?
Well, yes, you're right.
I don't know what to
All right.
do.
All right, there's two big ideas here. One of them is let's ignore that these are mins and maxes for a second. These are mins and maxes, but ignore that for a second. What they really are is points on a graph. They are points on a graph. If they're points on the graph, then I think if you plug this in for x, this is y. Do you agree?
Right.
If you plug this in for x, this is y. And which equation would you use to demonstrate that?
First one.
The first one, right. This is the function, right. This is x and this is y. So I think if you plug in a 0 for x, y is 0. If you plug a 4 in for x, y is 1,000.
Right.
I think I'm going to use both those ideas. Here I go. If I plug in a 0 for x, well, first of all, I just plugged in a 0 for y. 0 for y, then 0 for x. If you plug in a 0 for x, look what you get. They're all zeros, but you do
Except
get
for D.
d.
And d's at 4,000.
So you just find out that d is 0.
Oh, means
What did I just do? When x is 0, y is 0.
yeah.
That's what I did. And that's what I discovered. All right, let me try this other thing. When x is 4, y is 1,000. All right, let's try that. When x is 4, y is 1,000. All right, that means I'm plugging in 1,000 for y, and I'm plugging in an x. X is 4. Here I go. X is 4. 4 cubed is 64a. 4 squared is 16b. All right. And then 4c. And then I would have a d, except I already know
D is 0.
d is 0. So I'm not going to put that d in there. D is 0. All right, so now I got this idea. All right. Anybody got any other ideas?
Okay, so then,
Since these, so I covered that up and said, hey, dude, they're just points. If they're points, you plug them into the function. That's what I said. Okay, but now, more specifically, he is a min and he's a max, which meant that these x values are critical numbers. And if they're, well, you know, it's a min and a max, so it probably, what does a critical number do to the derivative? What does a critical number do to the derivative? It makes it 0. It makes it 0.
okay.
So now what I can do is plug these x values, ignore the y values, I already used those for what I needed to.
Okay.
I can plug these x values into the derivative, and I know that the derivative will be 0. Do you get that? They're mins and maxes. If you're a min and a max, the derivative is 0 when you're at that point. The derivative is 0. The slope of the tangent line is 0 when you're at that point.
Okay.
So when I'm at 0, here I go. When I'm at 0, here's what I'm going to say. When I'm at 0, when x is 0, the derivative is 0. That's what I'm saying. Not because that's a 0, but because it's a min. You with me? Because it's a min,
Right.
the slope is 0. So here I go, here I go, here I go, here I go. I'm plugging a 0 into the derivative, and the answer is going to be 0. Okay, I'm plugging a 0 in for x. That's a 0, that's a 0. Guess what I just learned? C is 0. Also, at this max, when x is 4, what do I know about the derivative when x is 4?
The derivative is 0.
The derivative is 0 because it's a max.
Right.
So it's a critical number. So the derivative is 0. All right, I'm going to use that. The derivative is 0 when I plug in a 4 for x. All right, here I go. That's 16 times 3a, that's 48a. I'm plugging in a 4 for x, that's 8b. And then there's a c out there, but guess what?
It's 0.
C is 0.
Yeah.
So now I have this piece of information. And by the way, I can go up here. This C is 0. So you know what I got here? 2 equations, 2 unknowns, A and B. 2 equations. I generated 2 equations, 2 unknowns. In a way, I generated 4 equations, 4 unknowns. But luckily, 2 of them were pretty darn simple. One of them was D equals 0, and the other one was C equals 0. But it was 4 equations, 4 unknowns. But now I'm down to 2 equations, 2 unknowns, and I'd like to keep solving, do some algebra, and find A and B. That's the game. You guys okay? There was concepts behind this game, but now the game is just algebra. I like that question. That's why I assigned them. I assign good homework problems usually. I mean, there's thousands of homework problems. I sifted through there and assigned what I liked and what I thought was relevant. There's plenty I skipped. This turns into an algebra problem, like I said. Now I'm trying to solve these 2 equations, 2 variables. What's this bottom one? Hey, on this bottom one, I'm going to move let's play with this a second. Move the 48a over. Negative 48a equals 8b. Divide by 8. b is negative 6a. I think I'll take that and substitute it in here. Let me go over here and substitute that. What did we just say? b is negative 6a? Okay, cool. I substituted. Now I can solve this. This is 64a minus 96a. That's negative 32a equals 1,000. If you divide, a is negative 1,032s. Or that reduces to negative 125 fourths, I guess. Cool. You guys okay? I found A. I already know D. I already know C. Where's B? Oh, there's B. B is negative 6 times A. So B is negative 6 times A. Okay. 375 twos?
Yeah.
All right, thank you. Dude, what do? We found a function that meets those requirements. That's pretty awesome. We found a function that meets those requirements. What is it? It is this with the A, B, and C, and D filled in.
The A, I mean here it is. It's the A was negative 125 force x cubed. The B was 375 over 2 times x squared. And the C and the D were both zeros, so that's the cubic function that meets these requirements. That's pretty awesome. It was a backwards question, totally. I mean, the frontwards questions are, I give you the function and ask you to find the mins and maxes. This was totally backwards. They gave us the min and max and made me find the function. I like that. Any other homework requests?
I just have a question.
Sure.
If you wanted to figure out what degree, could you also do like n being the degree, n minus 1 equals the number of your extrema, like 2?
I think so. And that reminds me of
For
pre-calculus
the
too.
lowest degree.
Right, that reminds me of my polynomial studies in pre-calculus where they would say, if you have degree n, what they always said was if you had degree n, you would have n minus 1 turning points.
Yeah.
That's the way they used to talk. Now, by the way, turning points are maxes and mins. It's where the function turns, I guess, and those are maxes and mins. So you're right. That's an old, polynomial theory idea. That whatever degree your polynomial was, it would have one less turning point, which kind of are the maxes and mins. So you're right.
I just couldn't do the connection.
Any other questions? Yes?
In 74.
4474. Oh yeah, I like that one. But those are always hard when it says think about it. But I like it. Let's think about it. Let's think about it. In 4-4, there's this 74, and they give me this picture of a vase. It's not a vase. It's a vase. And it looks like this. It's a vase. And what do they say? Water is running into the vase, shown in the figure, at a constant rate. Water is coming in at a constant rate. Graph the depth of the water as a function of time. Dude.
3.7.
So there's water in here, and the water's flowing into here, and then I got this thing called the depth, and they want me to graph depth as a function of time. Okay, you know what? You guys think about it.